We will continue our course by looking at some benefits and challenges with recirculating aquaculture system, RAS. We will also learn a few of the many real-world lessons from RAS failures in the past. What are the effects of RAS? To understand the benefits and challenges of RAS, we must look at various key components needed to maintain optimum water quality in the fish tanks, as we saw in our previous lecture. These technologies help to conserve water and show how complicated RAS can be. RAS systems highlight the need for expertise and what could go wrong if any of these systems break down. More technologies means that there is also a high risk of any of the systems failing if the necessary backups are not implemented. Now, let's discuss the benefits or advantages of using RAS in aquaculture. 1. High environmental control. RAS enables controlled growth rate and predictable harvesting. Temperature, salinity, photoperiod are some of the most critical drivers of the major physiological processes of the fish. These parameters and others can be controlled in RAS to ensure predictive growth and harvest when needed. 2. Water conservation. RAS uses up to 99% less water than conventional systems. 3. Smaller footprint. RAS is compact. It has an average fish density of approximately multiple times than that in cages and pond. Therefore, RAS allows for convenient deployment in population centers. 4. Proximity to market. RAS can be built anywhere because RAS help to deliver controlled and optimized conditions for the fish production. Fish can be produced closer to the demand centers, reducing transportation emissions. 5. High productivity. RAS is an intensive aquaculture system and has the highest production per unit area with effective waste management. More fish can be produced using less amount of resources. 6. Biosecurity and disease control. Through biosecurity, disease-causing pathogens are prevented. Therefore, there is no need for antibiotics in treating fish. Since no antibiotics are used, healthier fish are produced. 7. Sustainable management. RAS allows safe waste management, and sludge from fish waste can be value added. The sludge can be used to produce vegetables, biogas, electricity as an added revenue stream for the RAS farmer. This approach helps to manage resources in a more sustainable way. What are the challenges or disadvantages of RAS? While RAS has many advantages, it also presents significant challenges. 1. Lack of expertise. Operating RAS requires personnel with specialized skills and a readiness to respond quickly to issues. 2. Demanding work schedule. Staff must be available 24/7, including nights, weekends, and holidays. Therefore, staff agreeing to rotating staff work lifestyle is necessary. 3. Reliance on alarm and backup systems. RAS facilities depend on robust emergency systems due to high stakes in fish health. 4. Energy intensive. RAS requires sustainable energy for water movement and treatment, making it sensitive to energy price fluctuations. 5. High cost and risk. RAS is capital intensive and seen as high risk investment, which can deter investors. A poorly designed RAS and poor operations will increase OPEX to a point where the economy of scale tip in the wrong and unexpected direction. 6. Developmental challenges. RAS technology is still developing, which carries risk including potential fish losses. What are some of the lessons learned from past RAS failures? RAS have experienced notable failures, often stemming from complex operational challenges. Lessons from the past RAS failures highlight the importance of proper management and robust system design. Here are some few examples. System failures and fish mortality. In early trials of moving salmon farming from sea cages to RAS, catastrophic system breakdown led to mass fish mortalities. These failures were often due to issues in managing water quality parameters such as ammonia and nitrite, which can quickly reach toxic levels if biofilter is inadequate. As fish density is high in RAS setups, small disruption in filtration, electricity, and oxygen supply can lead to rapid and large-scale fish losses. Idaho-based RAS farm lost over $20 million and closed its RAS farm after just 2 years of operation due to an inadequate biofilter capacity. Also, Fish and Dakota RAS farm also suffered a major loss after emergency systems were removed, underscoring the need for robust backup systems. A farm in western Pennsylvania had to close when a catcher tank liner broke, leading to system failure. In another case, improper cleaning of a fixed bed resulted in H2X buildup, killing all fish in the system. Another lesson learned is on disease-causing pathogen introduction to RAS, an outbreak linked to improper biosecurity barrier. It is also difficult, if not possible, to remove these pathogens after they have matured in the RAS system, especially in the biofilters. Therefore, proper RAS design with efficient biosecurity consideration will enforce biosecurity in RAS. In addition, careful monitoring to prevent pathogen accumulation will ensure necessary measures are taken to avoid reaching catastrophic levels. In conclusion, RAS is promising for the future with its sustainability offering, but challenging aquaculture method. The benefit of high productivity, water and land conservation, and biosecurity make it a sustainable choice, but it requires careful management, significant investment, and skilled personnel. This is why this course is designed to give RAS designers and operators the necessary expertise to avoid expensive mistakes. I hope this section has been informative. See you again in our next lecture. Thank you and bye for now.